On clear, cold nights, ribbons of light ripple across the polar sky. The northern lights feel ancient and otherworldly, yet their glow follows the laws of physics. To understand their beauty, we start 150 million kilometers away at the sun. This episode explores the science behind the aurora borealis and the human stories beneath its glow. From solar storms to Sámi legends, from atomic collisions to blackouts, the northern lights link space weather with life on Earth. The sun is a fusion reactor, fusing hydrogen into helium and releasing energy. Along with light, it throws off a constant outflow of charged particles called the solar wind, streaming outward at hundreds of kilometers per second. Sometimes the sun erupts, sunspots brood, magnetic fields snap, coronal mass ejections hurl plasma into space. When these clouds aim at Earth, they can supercharge the aurora and set the stage for magnetic storms. Earth's magnetic field is our invisible shield. It deflects the solar wind and stretches into a teardrop magnetosphere. Most particles are turned aside, but some ride field lines toward the poles. Near Earth, magnetic reconnection and electric fields accelerate electrons. Spiraling down field lines, they strike the upper atmosphere above the Arctic and Antarctic, depositing energy that becomes shimmering curtains and fast-moving arcs. At the atomic level, electrons strike oxygen and nitrogen atoms and molecules, kicking their electrons into excited states. As they relax, they emit photons. This is auroral light, quantum jumps written large across the sky. Color reveals altitude and chemistry. Oxygen at about 100 to 150 kilometers glows vivid green. Higher, around 200 kilometers and above, oxygen yields deep red. Nitrogen paints blues and purples, outlining edges and forming rippling fringes. Forms tell a storm's mood. Quiet nights show steady arcs on the horizon. Substorms erupt into waving curtains, rayed bands, spirals, and coronas overhead, pulsing and racing along magnetic lines. The aurora gathers in ovals centered on magnetic, not geographic poles. When space weather intensifies, the ovals widen and drift equatorward. Forecasters track this with KP, a scale from 0 to 9 that guides where lights may appear. For every northern display, there is a southern twin, the aurora australis. From space, astronauts see paired ovals ringing the poles, glowing like planetary halos. On the ground, geography and clouds choose who gets the show. Long before satellites, people told stories. Sámi herders stepped softly beneath the lights. Norse sagas imagined Valkyries' shields. Inuit tales spoke of spirits at play. Awe was universal and quiet respect filled the night. Elsewhere, Chinese and Japanese chronicles recorded crimson skies. Medieval Europeans saw blood-red nights and bad omens. These written accounts, scattered across centuries, now help scientists reconstruct past space weather and the reach of historic auroras. In the early 1900s, physicist Christian Birkeland built a Torella, a magnetized sphere in vacuum. Electron beams traced glowing rings around its poles, a tabletop aurora that hinted at electric currents flowing in space. The space age proved it. Satellites measured particles, fields, and vast Birkeland currents linking space to the polar atmosphere. Missions like Themis and Cluster watched magneto-tail reconnection trigger substorms and unleash the night's drama. People sometimes report hearing auroras crackle. Sound from those heights is unlikely to reach the ground, but faint rustles near the surface may form in rare conditions. Research continues, balancing folklore with careful measurements. To see them, chase darkness and patience. Leave city lights. Check a clear forecast in the solar wind. Around the equinoxes, chances improve. When alerts rise, step outside, face north, and let your eyes adjust. Where you stand matters. Under the auroral oval, Alaska, northern Canada, Iceland, Greenland, and Arctic Scandinavia. Farther south, strong storms can push lights over Scotland, Germany, the northern United States, and beyond. Cameras reveal more than eyes. Use a tripod, a wide fast lens, and manual focus at infinity. Try ISO 1600 to 3200 with exposures from 1 to 10 seconds. Shorter for fast curtains, longer for faint arcs. Auroras are harmless to people, but the storms that power them can disturb technology. Geomagnetically induced currents stress power grids, disrupt radio, and heat satellite atmospheres, increasing drag. In 1980, a storm blacked out Quebec in seconds. The strongest known event, the 1859 Carrington storm, lit telegraph lines on fire and pushed auroras to the tropics. A modern repeat could challenge navigation, power, and internet infrastructure. Forecasting and hardening systems are our best defenses. In the end, the northern lights are a bridge. They tie human wonder to the physics of stars and fields. When the sky begins to move, we are watching space touch Earth and hearing the universe speak in color.